There's no mic. You can just talk.
Okay, welcome everyone to the 33rd SIS talk. So today our speaker is Anuraj. We are from
That's
Mathematical Sciences, and he'll talk about he'll talk about tree coloring and art group. So Anuraj, please take it.
okay. So yeah, it's going to be a pretty long talk. I mean, so I'll tell you whatever we are going to discuss. In the start, we'll just talk a lot about combinatorial aspects of knot theory, and then I'll explain what tree coloring is and how to compute tree coloring for a random knot. And in the end, I'll talk about a little bit about algebraic topology and how the idea of tree coloring comes from knot groups. Okay, so I mean, at any point, if I am too loud, please tell me to uh, tone down. Okay, so let's go to our main question. What the hell is a knot? So for now, I'll give you a very simple definition. A knot is just a string which you take and you move around however you want. You can do whatever you want, but in the end, you just have to join both the ends together. Then you have a knot. So one of the basicest of knots you can think of would be a circle. You take a string, connect the two ends, you get a circle. And one another note is this trefoil. I've written there. That's 5-2. It has some name. I don't know. Like, okay. So you might be thinking, okay, what is the problem here? So the problem is I can do whatever I want with my string. So how do we know if I give you something like this? If I give you a knot like this is an overcrossing and this is an undercrossing, a string like that, I can just tell you, like, you do something, you just twist it and it's a unknot. Okay, so then what is the point of taking this and this as two different knots? They are just the same. So, but in fact, the trefoil, no matter whatever I do, I can't get into an unknot. So our main question is like, how do you categorize these knots? How do you put them into equivalence class? So you will be asking me, okay, what do you say by, what do you mean by equivalence of knots? Like, how do you make it more precise? That also, I won't give you a precise definition, but a vague definition would be, I have a knot, I have another knot. If I take this knot, I just, wiggle it around, and then if I can get the other knot, then wiggle it, twist it, move around, and then get the other knot without, cutting or gluing the string. I can say these two knots are equivalent. Fine? Everyone fine with till here? Okay. So the problem with this definition is I can have, infinite knotting. I can have this and then I have some knots here, knot here, and then I can have the same knot and then just a decreasing series of infinite knotting. I mean, I didn't say that I cannot infinitely keep on knotting and then attach it together. That is very hard to see, very like you cannot count the number of crossings or like it's very hard to understand. Also, for the equivalence of knots, I said like you can just move around the string. What if I take a knot and then there is a knotting in the middle and then I start pulling the string. So it will keep on shrinking, right? So there are functions which are equivalent to this pulling, which gives me after a very long time, after infinite time, I can get this whole knotting into a point. So I can just say every knot I can just pull it like for infinitely long time and make it a unknot, make it a line. So there are problems with these definitions. But before going into more precise definitions, I want to categorize into two types of knots. So I'll have knots as wild knots and tame knots. Wild knot is just wild like this, infinite knotting and all that stupid stuff. Tame nodes are much more friendlier, and by friendly I mean tame nodes can be expressed as a polygon. Like I can, for a circle, I can just do this like a polygon. For a trefoil, I can actually have something like this. Yeah, something like this for the trefoil. This is a polygon. I have a equivalent node. So now now you tell me, how do you define equivalence of tame nodes? Polygon is just okay. Uh, what do you say? Mm, like square, triangle. Yeah, it's just that. Fine. Yeah, for our purposes, that's enough for a polygon. Okay. So where were we? Yeah. So how do you define equivalence for these polygon nodes? So if I for that, I'll introduce the concept of delta moves. So what is a delta move? If I have a piece of knot like this, so I take a piece of knot like this, and then I just do this. I just I just cut out the middle part and then add a vertex and two edges. It's almost equivalent to just moving it a little bit. But for a more precise definition would be of this. Fine. I can do the reverse also. If I have something like this, I can just cut this unnecessary thing and make it like this. Fine. Everyone fine with that? Okay. So the problem is I was telling you to move the string around in 3D space and just put it together. But it's very hard to look at 3D knot. So what we will do is we'll try to get it down into 2D. We'll try to take the projection onto a 2D plane and try to understand it. So okay, so we have a polygonal knot, and then we try to put some light on top of it to get in a plane, any random plane you take, and you try to get a projection. So usually what we expect is that we have a line like this, we have another line like this, and then it just projects into some good crossing. But the problem comes where I have something like three lines, three lines all on the same line. There also I can get something like this. I'll get all in the I'll get all in the same point. This is not same as this. What I we can call this regular projection. This is regular projection, and this is irregular. Also, you can have stuff like this, which will just go into a point. Like if I'm lighting from here, this will just project it as a point, right? Yeah. So to get away from stuff like this, we'll introduce something called epsilon perturbations. Yeah. So what is epsilon perturbation? Epsilon perturbation is like you take the knot, you just move it around a little bit, epsilon distance. So the interesting thing is, like if I take something like this and then move this around, move all this around in a particular way, I can get a regular projection from this, right? I can just move this around in a particular way so that only two of them lies in the two of the point coincides and one just moves away a little bit. Similarly for this also, I can just move this a little bit so that I'll get a proper regular projection. So in fact, regular projections form a dense set in the set of all knots. I mean, if you don't know the definition of dense set, don't worry about it. Just understand that From any regular projection, you can just get into regular projection. That's more than enough. Set of all nodes or set of all nodes? Like set of all polygonal nodes you can take. Hmm? No, 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 no. You study real analysis, right? Yeah, there's more to it. You don't. Huh? Space of all nodes. What's the problem? Like, huh? Not. Like, I'm not understanding the question. Huh? Okay. I told like you take a what? You take a random polygon in 3D space. Yeah, then you can consider it as a knot. Yeah, I mean we are just talking about polygons right now. Yeah, yeah, polygonal curve. Yeah, fine. Okay. So, hmm, I mean, the idea of upsilon perturbation is that only like you can find a very small within a small move you can get to this. Yeah, I mean more precise definition. I also don't know. Yeah, we can figure out, I guess, with to if you want a more precise. Huh? Yeah, that I'll comment on. Okay, so that gives us something very interesting. So every knot which has a regular projection will have a diagram. So a knot diagram is just this or this, or yeah, just that. This is not a 3D thing, right? This is a 2D drawing. So this is a 2D drawing of a 3D trefoil knot. So if I have a regular projection, I'll get a diagram. Fine. So the good thing is that if I have a diagram, I can build back up the knot up to equivalence. Fine. From a diagram, I can just find whatever the knot is up to equivalence. Like I can see that there is an overcrossing, there is an overcrossing, there is a undercrossing, and all that. I can just get the 3D idea of the whole knot from a diagram itself. And yeah, so for irregular also, you can just do epsilon perturbation, get a regular projection, find the what the equivalent knot of the projection. Fine. Okay. So what interesting thing happens here is that so we have a yeah, so we have a polygon knot and say I have something like this. Um, Now I do a delta move like this. Fine. Now, if I ask you, what will if I take the regular projection, like from here, this just went from here to yeah, here to yeah, here, right? This is went from here to here using delta move. If I take the projection, what will happen? I will get the first Redomaster move. So the Redomaster move, I mean, do you guys know about Redomaster move? No, it's fine. Okay, so yeah, I love okay. So when you are taking the projection, you're doing the delta move and taking the projection. You know, when you do a delta move, you are getting an equivalent knot, right? So if you so before doing the delta move and after doing the delta move, the projections should define the same diagram. Fine. So this is before doing the delta move. This is after doing the delta move. So if I do the take the projection of this and take the projection of this, they define the same diagram. So that's what Redomaster moves in diagrams means. Like this is a straight line, which it will be same as doing one twist. Yeah, you can say twist. Similarly, I can similarly I can have something like this. and then I do a delta move like this, then I'll get something like this, right? Which is actually the second Redomaster move. Fine. So delta move we are doing on the 3D space projections, sorry, 3D space polygonal nodes. Equivalently, we are getting a Redomaster move. Fine. Equivalently, we get a Redomaster move of diagrams. We are doing this on the plane, on the 2D surface. We can do this and be fine with it. Similarly, for R3 also, there is, yeah, you can have, if I have something like this, yeah, if I have something like this and then I do a Redomaster move like this, I'll get, this, which is moving off. Yeah, fine. Yeah. Hmm.
Not understanding how you take the
Okay.
if it's in a 3D plane, you can take projections.
Yeah, anywhere you can take, but I decides to take like this. See, you can have a lot of projections. What I want to see is that what are all the main cases that will form when I take the projections before and after a delta move. Like I decide to take the projection like this, then I get a case like that. I mean, I'll get way different diagrams, but almost all of them will be equivalent because, yeah, all of them will be equivalent because it doesn't change anything specifically. We are just looking at it in a different direction. Okay.
Each particular projection, you will get a and they all will be.
Yeah, I mean, see, for a knot, you can get a lot of projections. What I want to talk about is like now we want to get away from this 3D space. We are looking at 3Ds and then we don't want to know about it. So I'm trying to find analogous stuff in 2D plane. Like so, when I go into 2D plane, I need something analogous to delta move. I don't have something proper delta move there. Because delta move here didn't obstruct anything or there was no problem here. But here it will get obstructed because we are looking like delta move will be on a different plane. But when I take the projection, both should be in the same plane. So I need to get something analogous in 2D so that I can work with 2D only. I'll forget about whatever 3D does. Hmm.
How do you decide which direction?
That's what I already decided. You can take any projection.
And all any projection you take the very much
No, see, randomizer move. I'm not looking at a specific knot here. I'm just looking at a specific case. Take a random knot, and if I do a delta move like this, and then take a projection, I'll get something like this. I don't care which knot it is. I'm just looking at a piece of knot. I just want the what equivalent of, I mean, equivalent definition for delta move on a plane. Hmm.
depending on which side you take the projection, you get different.
Yeah, I just decide to take the like from this side. Yeah, I mean there are many cases, but almost all the cases will come down into these two, three specific cases. Fine. Any more questions? Huh? Yeah, third one, this one. Like I have something like this, and then hmm? I have a see. I have a crossing in 3D. I mean, just see it in 3D. Just take anyone above. Like it's in 3D. That's what I said. Like okay, you have 3D, and I have a one more line on top of this. Yeah, on top of all this. On top or below, anything is fine. Yeah, on top. Suppose I have on top of all of this. Now I take a delta move like this. Huh? Then it's same as moving through the lines in diagram. Fine. Yeah. See, these are very intuitive in case of diagrams, but I just wanted to give like where that comes from. It's not like it's not directly we decided to okay, we'll just do this and that. Okay. So yeah. So this gives us a very good equivalence, which says that polygonal nodes in R3 by delta move equivalence as a bijective correspondence between what diagrams in R2 by what Redemaster. Redemaster move equivalence. Okay, it's just that like you'll have a bijective correspondence between these two. Fine. Okay. Now we'll go on to define something very interesting. We'll say what is an invariant. So an invariant is a function which, I mean, in this case, invariant is a function which takes uh, two equivalent knots. So I say invariant, say I is a function. I have k and k dash equivalent knots. Then I of k will be equal to I of k dash. Fine. If I have k and k dash are equivalent, I of k is equal to I of k dash. But the problem here is if I have I of k1 equal to I of k2, this does not necessarily imply that k1 is equivalent to k2. I can have same value for invariant for not equivalent knots. But if it's equivalent, invariant value should be same. Fine. So it's better to use equivalent, I mean invariant to find non-equivalent knots rather than to find equivalent knots. Fine. Like if I get a different value, then I'm sure they are not equivalent. Fine. Okay. So from here we'll go to the three coloring equivalent. I mean invariant. So three coloring invariant says this. You have a knot, and then what you have to do is you take three colors and you have to color this knot. Hmm? I take a piece of knot. So there is only there are two rules for coloring. In every crossing, either all these three colors should be same, or all these three colors should be different. That's the only rule we have. So if I decided to use red, blue, and green, I can have red, 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 or red, blue, green in and any combinations of this. Okay. So like, how is this an invariant? Like we have to prove this is an invariant. How do you prove that this is an invariant? Okay, I'm taking a knot diagram and coloring it. Fine. I have showed that the equivalents come from Redomaster moves. So if I say that the three coloring for two equivalent knots means for two equivalent knots, the three colorings should be same, then I'm done. It's an invariant, right? Okay. So if I can prove that for all these, yeah, if I move from here to here, my three colorings won't change for all these three cases, then it's an invariant, right? Okay, so I mean, it's a bit tedious process. There is a Veritasium video on it if you want to. I mean, there it's the idea of proof is given, or I'll send you a PDF about all this stuff. Okay, fine. So for projection diagram for a diagram. Mhm. Mm. Mm. I'm not putting it. Hmm? Mm. Yeah, two different arcs. Part of. Yeah. Yeah, that we are. If I say this is a projection. Like when you say a projection, you are saying that you are looking from here, and then only you are taking the diagram, right?
It's, when you're retaining the information that is
Yeah, that will always be there. Yeah. So, okay. So the main question I wanted to ask is, okay, before going for an unknown, how many three colorings would be there? It would just be three. I mean, red, blue, or green. Yeah, but for a trefoil, there are nine three colorings. I can have red, blue, or green, and then I can have different colors for each of these arcs in six permutations. Right? Then nine colorings. I'll give you a how to do that in a bit. Okay. So our main problem is that where does this random rule come from? Like why can't we just color this one and I mean color this and this the same and this different? That we are going to look in a bit. Now what I want to talk about is okay. Let's see. So I take a knot with uh, M marks and L crossings. Yeah, M marks A1 up to AM and L crossings C, C1 up to CL. Okay, and so now if I name the arcs A1, 382, something interesting you can see that if I put A1 equal x1 plus x2 plus x3, now if I assign a value x1 for a1, x2 for a2, x3 for a3, and then if I take these x1, x2, x3 from the field of three elements, field of three elements what? 0, 1, 2, right? From the field of three elements, I can get the same exact rules. I mean, x1, x2, x3 equal to 0 will give me same exact rules as this. Because to get it 0, I need all of these to be same, like either 0, 0, 0, 1, 1, 1 or 2, 2, 2, or all of these to be different. 1, 2, 0, 1, 2 should come. Fine. So that gives me something very interesting, which is this defines a vector space of okay, I'll just write it there. This defines a vector space of x1 up to xm S3M such that xi plus xj plus xk equal to 0 for crossing arcs for yeah crossing arcs ai aj and ak, right? Think about this, like I can for each arc I can assign a value from field of three elements, and then I can say this rule where I add this up, it should be 0. Then this would be an element would be a specific three coloring of the knot. Fine. Now, how do you compute this? Now, okay, think of this as a linear transformation from F3M to F3M. Like, okay, now if I can write a TD of x as AX, huh? AX equal to 0. Yeah, okay. So I write TD of x as AX. I'm writing T as a linear transformation. Fine. As AX, I'll make sure what exactly I mean. AX, okay. So if I can write it as AX equal to 0, the nullity of the matrix. Okay, before telling this, I'll tell you this. What is the number of elements in T of D? Number of elements in T of D would be number of three colorings only. Fine, which is equal to 3 raised to the power dimension of T of D. Right? Okay. Now think of it. I can okay, you understand dimension of a vector space, right? Okay, so for each element I need what? For each element I'll have dimension number of bases. So for coefficient I have three options. So 3 3 3 3 3 3. Fine. For each element I can specify it as basis 1 into some coefficient plus basis 2 into some coefficient, and all these coefficient will be taken from F3. I have three options all the time. Then 3 raised to the power dimension T of D. Fine. Okay. Okay. So for okay, now I'll write it like this. Hmm. Hmm. Yeah. Which no, I'm just taking a basis. I'll have a random. I'm fixing the vector space. This is my vector space, and then I take a basis. I'm taking the dimension of T of D. I don't care about anything else. Okay. Yeah. So if I write it like this, and now the nullity of A gives me the kernel of T. Right. Okay. So what is T here actually? So let's look at T. So for this diagram, my A matrix would look like this. I take a point, or I'll explain it in a different way if I know. So now think of T as solving, how many crossings we had. Yeah, L linear equations. Hmm. So like it would come as like a1 x1 plus up to am xm equal to 0. Yeah, then we have al x1 plus. No. Yeah, what? A11, A1M, AL1 and ALMXM equal to 0. Like you will have L homogeneous equations. Fine. These L, okay. So if I say this is what defines my vector space, will you agree with me? At each crossing, we will have an equation like this. Like okay, see, so this A1 AM, okay, I'll show you how I define that. Now I have yeah, I'll define a matrix A for this diagram, which is okay. So at first I'll look at the crossing number 1 and which all arcs are converging into that crossing. So here 1 1 1. So first arc, second arc and third arc are converging in this crossing. So I'll just put 1 for each of them. Similarly for the second one, also I'm having 1 1 1. Third one also I'm having 1 1 1. I mean, let's look at this for a much more interesting thing. I'll have, okay, for the first one, we are converging 1, 2 and 3. Can you see it? Yeah, so 1, 2, 3, 0, 0. And second one, it's 2, 3 and 5, I guess. 2, 3 and 5, like that. So this is my matrix. So now this thing makes sense, right? I'm just adding up all the places where, so this A1 will be 1 for if xi is in the crossing, otherwise it's 0. Then if I compute the nullity, that would be the kernel of the ax equal to 0. that would be the dimension of kernel of X equal to 0. That is exactly what we want. We need this equal to 0, right? I mean, yeah, that is exactly what it defines. Because we need, yeah, so it actually shows this L homogeneous equation actually defines this. Whenever there is a crossing, I should get 0. Yeah, but I'm defining it like this. I mean, yeah, so from here, you can do Gaussian elimination, and then you can't get the value 2 because I'm defining it like this. I mean, from the making. I'll just put 1 whenever I have a crossing. Just that. Yeah. Yeah. Now, I don't care about 2. But- yeah, because field of 3 satisfies this condition x1 plus x2 plus x3 equal to 0 whenever I have all the three same or all the three different. I mean, you can write 2, 2, 2 and go on. You'll get the same thing. I'm just putting 1 so that it's easy to see. Yeah. Okay. So, oh, yeah. Hmm. Yeah. First randomizer moves. Yeah, there are two arcs. Yeah. Hmm? You, yeah, like you cannot three color it because it's in the same arc. That's how the equivalence comes. Like that's how you prove the invariant. It's shown that like if this is one color, that defines the color for this. If this is in a coloring, that defines it. So it cannot have two coloring. I mean, due to our rules. So you understood this, or what? Okay. So we'll make a matrix like this, which helps us define the vector space. Fine. And the nullity of matrix will give me the dimension of the vector space. Okay. Yeah. So how do you get the nullity of this? You just do Gaussian elimination and then you will get 0, 0, 0, 0, 0 here, 0, 0, 0 here. Fine. I get nullity equal to 2. What is the number of elements in this vector space? Yeah. Yeah. Okay. A, yeah, that's what. I'm making a matrix specifically for this. Yeah. X is an element from X1, like X is a random element from F3M. Like, yeah, I'm looking at the X is a what? I'm looking at the system of equations. X equal to 0. System of equations. Yeah. I mean, system of equations defines the three coloring actually. See, the homogeneous system of equations defines. Yeah. Uh-huh. Fine. So, hmm? I mean, what? Yeah, undercrossing or overcrossing what? Yeah, I don't care much about if it's an undercrossing and overcrossing. I just need a crossing here and here. Like I don't have much to do with if it's an undercrossing or overcrossing. Yeah, that's one very important thing. If I take the mirror image of this, then all the undercrossing will change into overcrossing. Hmm? Hmm. Hmm. Yeah, you just flip it, right? No. Yeah. Oh, just that one. Yeah. That will change the meta. Then the whole thing will change, no? Fine. Okay. So I'll get nullity as 2. Then 3 square equal to 9 would be the number of elements in the vector space. 9 would be the number of three colorings. Fine. Yeah. Oh, we have been taking a lot of time. So from here, we'll move into something way more interesting. We'll talk about topology. We'll talk about the topology of knots. Okay, from here, I'll give a much better definition of knots. Think about, okay, so from now on, if X is a topological space, I mean, how many of you are not familiar with topology? Okay, so just now for our practical purposes, just think of, when I say topological space, think of R3, R2, S1, which is a circle. S1 is a circle, S2 is a sphere. S2 is a yeah, three-dimensional sphere, and S3 is a four-dimensional sphere. Okay, just think of these three. I mean, topological space has a much more general definition. You don't need that. I mean, for our purposes, we don't need that. So X is a topological space. Then a subset of X that is what? That is homeomorphic to a circle. Okay, you know what a homeomorphism is. Okay, a homeomorphism is a function which is continuous and bijective. H करते हैं. Continuous and bijective, which has its inverse also continuous. Right? If I say two spaces are homeomorphic, that means I have a function going from one space to another, which is continuous and bijective, which has an inverse which is also continuous. Fine. Okay. So I say what? A node, a node K is a subset of the topological space X, which is homeomorphic to S1. Right? Okay. So if you want, we can have one more definition, which is K is a map from S1 to X, which is an embedding. I mean, just yeah, a homeomorphic image of S1 to X. Fine. I mean, you might be thinking like, how does this come from our first definition of knots? Like from connecting strings to how does it come to homeomorphism between a circle? So you, if you know quotient topology, it would be something like, okay, a string for us is just 0, 1, the interval 0, 1. You can just move it around, you can pull it and you do anything with it. Yeah, 0, 1 equipped with the quotient topology, where yeah, 0 is equivalent to 1. So by, okay, for people who don't know quotient topology, it's the idea is that we are trying to put things in an equivalence class. So we have a big thing and then we try to put some points in an equivalence class. It's the same idea of gluing. We take 0, 1 interval and glue 0 and 1 together and we get a circle. Fine. I mean, one classic example is like you take a disk and then you put all these boundary points into one equivalence class. And you don't do anything with the interior of the disk. Put all the boundary points into one equivalence class. Then it will all go into a sphere. Then the disk will become a sphere. Fine. Okay. I mean, it's not. Anyway. Yeah. So we have, yeah, we'll use this definition. So node for me from now on is a map from S1 to X, from a topological from a circle to a topological space X, an embedding. Now, what is, you will ask me about, okay, now what is the notion of equivalence? So notion of equivalence is a map H from X to X such that H of K1 equal to K2. K1 and K1 and K2 are equivalent knots if I have a homeomorphism from X to X, homeomorphism from the space to space, which specifically takes this to this. Fine. Okay, so there is a little more stronger definition of equivalence that will come to later. Now, what we want to do is, yeah, I want to introduce the, okay, so before going into that, the main question that comes in topology is that, so we have these random spaces, like just like knots, how do we put them in equivalence class? So the answer is finding homeomorphism between them. But the problem is it's so hard to find homeomorphism between spaces. Like you have like really messy homeomorphisms, and a lot of problems arises while you're trying to find homeomorphism between two spaces. So what we came up with is that we can associate a topological space with some algebraic object, then look at that algebraic object and say if it has homeomorphism or not. One of those uh, ideas is that the idea of fundamental group. Like that is you take a topological space and associate it with a group. That we'll see the details in a little bit. So I want to introduce you to the concept of homotopy. Okay, what is homotopy? So I have topological space X and Y. Huh? Now the a homotopy is a map from X cross 0 comma 1 to Y such that H of S comma 0 is f of S and H of uh, S comma 1 is G of S. Like you can think of it as like oh sorry. So if I have a continuous function f going from x to y, g going from another continuous function g going from x to y. A homotopy between these two maps is a function, is a continuous, is a what is a family of continuous function from x to y that that takes h of s comma 0 f of s as h of s comma 1 g of s. Like you can think of it as h subscript t. Like this 0 1 interval you can think of as time. So you are continuously deforming the function f into getting into g. Fine. So for our purposes we need a special kind of, yeah, it would be some kind of function that you can define it. I mean, I'll show you a much more visual idea of this. So now if I have two paths in a space, if I have f from x to x to y only, and g from, just I'll take x to x, g from x to x, and f of 0, okay, and f of 0 equal to g of 0 and f of 1 is equal to g of 1. So I have a, say I have a topological space like this x, and then f is a path from this to this, and g also is another path from this to this. Fine. F of 0 is same as g of 0, f of 1 is same as g of 1. Fine. Now the idea of path homotopy is that similarly, now I'll use t variable if you want, x to x such that h0 of s is f of s only, h1 of s is g of s, and h0 of 0 is equal to f of 0 equal to g of 0, h1 of 0 is equal to, yeah, h1 of 0, so 1 of, yeah, 1 is equal to f of 1 equal to g of 1. So what I'm trying to define is a family of functions like this. I'm trying to slowly move these paths around to get into this. You got the idea? This is what homotopy trying to say. I mean, path homotopy trying to say. I have two paths from one place to another. Now I am trying to slowly move one into another. So homotopy gives me a much stronger notion of equivalence, which is called ambient isotopy. I'll just say whatever it is. Ambient isotopy is a homotopy from say x to x such that h of 0 is the identity map, h1 composition k1 is k2. This is the idea of ambient isotopy for knots. Yeah, I mean, if you are not getting it, leave it. It's not a. I'm just giving the idea. Okay. Now we'll go into a very interesting thing called fundamental groups. So say I have a topological space. Uh, yeah, homotopy is a family of maps. Yeah, yeah. I mean, yeah, I mean, you can see this as one full map. No, no, it's a specific map I am defining. Yeah, this is a homotopy. You can see it as a function only, a specific function from this to this. It's better to see it as a family of map just continuously moving from this to this. Yeah, oh, and every HT is a homeomorphism. Yeah, okay, fundamental group. So I have a topological space X, suppose. Now I take a point, base point x naught. What I want to do is to look at all the loops I can draw in x naught. Fine. Now what the problem? Okay. So I draw a loop. Now I draw another loop. Now you guys will tell me, okay, you can just find a homotopy between these two loops. I can just deform it into, I can just shrink it into this. Now, what if I have a hole here? Then I cannot shrink further because there is no place to shrink. Right? If I have something like a hole, and I will have another loop here. So what the okay? Now I take all such homotopy classes. Homotopy class means I take all these things in one equivalence class. All the loops that can be that are homotopic to each other in one equivalence class, although are homotopic to each other in another equivalence class. What interesting thing we also observe is that these homotopy classes form a group. That is the interesting stuff. So how do you will ask me, okay, what is the operation? So I have x naught, I have homotopy class represented by f and homotopy class represented by g. Then what is the group? I mean, what is the binary operation in the group? That is concatenation of loops. So I'll start from here, go here, come back. That is a loop. I mean, okay. So the idea of loop is that a function which f of 0 equal to x naught equal to f of 1. A path with f of 0 equal to x naught equal to f of 1. Okay. So here I'll have f of 0 equal to this x naught and f of 1 is equal to x naught, g of 0 equal to x naught, g of 1 is equal to x naught. What I'll do is I'll make f twice as fast. I'll define f as instead of I'll do f of 2t and g of yeah, I'll just define h of t as f of 2t and g of 2t minus 1 minus. Yeah, 2t minus 1. Yeah. From 0 to half and half to 1. Now what I'll have? I have f going twice as fast and then g going twice as fast. Huh? T is just okay. So a path means a function from 0 comma 1 to x. So I'm just using time to show this variable. I can just say x only, it's fine. So Now I have a loop H, which is the concatenation of these two loops. Fine. Are you guys fine with this? Okay. So, okay. Now, now you guys will ask me, okay, what is the identity element? Identity element is just not moving at all. Just the point x naught will give me the identity element. Just f of 0, 1. 0, 1 is just x naught. Fine. What is the inverse? Inverse is just traveling opposite direction. Like I specify a direction for path. Like I just swap this into this. Like 1 minus t. Instead of writing t to that, I'll just write 1 minus t. Means I'll travel in the opposite direction. Fine. Okay. So once this is done, okay. So now you guys will ask me, you're talking about groups and all that stuff. Where is the homeomorphism coming from? I told that by associating it with groups, you can easily categorize you can easily put topological space into equivalence class. Now, what interesting thing happens is, if I have x and y, and I choose base point x naught and y naught, and I have a continuous function f going from f taking x naught to y naught. What can I do is, if I have a loop here, that will define another loop here, right? You guys fine? Like, what do you say? Mm, yeah, f of 0 will go here. If I have some g here, then f of g will give me a loop here, because as as I travel through this, I'll start putting points from there to here. Fine, it's a continuous function, so everything will go smoothly. Now, okay, so this will give me, so the fundamental group of this will be pi1 of x comma x naught, and this is pi1 of y comma y naught. Okay, so when I have a continuous function f going from x to y, I will get a homomorphism from from going from this fundamental group to this fundamental group. Okay, so now what if this f is a homeomorphism? Then I have a continuous function going from this to this and a continuous function coming from this to this. So I'll get a two-way homomorphism, which gives me an isomorphism. Fine. Everyone fine with that? Okay. So yeah. So if I get f as a bijection, sorry, f as a homeomorphism, then I can have an isomorphism of fundamental groups. So that's how we can easily look at that. Look at fundamental groups, and if two topological space are homeomorphic, their fundamental groups will be isomorphic. Fine. Like an example of fundamental group, you can see for a circle, what will be the fundamental group? You start at a point, and then start wrapping around it once. Like I can go till here and come back. That I can pull down into just a point. But what if I just cross this point and then go here and come back? I can pull it till here, but then I cannot pull much. Just think of a tree and trying to wrap a rope around that tree. Like once you don't complete the tree, you can just pull it back up. But once you wrap it around once, then you cannot pull back the rope. And then you can wrap it twice, wrap it thrice, and they are all not homotopic to each other. If I wrap it twice, then I cannot pull it back and make it wrapping it once. So they are all what? They are all different homotopic classes, and I can do the opposite way also. So actually, fundamental group of S1 will give me integers. Can you see how it comes? Similarly, for a torus, you can torus fundamental group will be Z cross Z. I mean, you can intuitively think about it like you can wrap like this or go like this. Fine. Okay. Now, I'm too tired. Should we do it some other day? Anyway, so now, okay, we went a lot far away from knots. Now we'll come back to knots. Now, now just only think about R3, knots in R3. So we don't want to. So all the knots in R3 are homeomorphic to S1. That's not fun. I mean, what will we do with that? So what we do is we just take R3 with knot in it, and then we'll just remove the knot. We just take out the knot from R3 and then compute the fundamental group of that space. Now, I mean, you can see that it would be very hard to think about it, but there is a much more interesting way, much more easier representation of this knot group. So, knot group will be phi1 of r minus k will be the knot group. Fundamental group of the complementary space is the knot group. Fine. Okay. Now, huh? K is the knot. I mean, whatever knot we wants to compute. Yeah. So now there is a very interesting representation. So you take a knot diagram. Hmm? And okay, how do you compute the fundamental, I mean, knot group of this knot diagram? So each arc you try giving names. Hmm? And then just think of a point in 3D space. Then you will have a what? A string going like this, going under the crossing, all the loops going under the arc X, and all the okay. Sorry. So we'll fix the direction first. So you take an oriented knot, and then we just fix the direction that this is right hand wrapping direction is the direction my loops are going. So my loop is going this way in X. Similarly for Z, my loop is going this way. I mean behind the string. In Y also, uh, we'll have this way and this way. Fine. Now, now, if you observe something that if I connect these two loops, this the loop wrapping around X and wrapping around Y, I'll get a full loop just going around these two strings. Similarly, if I connect loop wrapping around Y and loop wrapping around Z, I'll get a loop that is going behind the whole crossing thing. That loops can be homotop to each other because they are completely lying behind the crossing, right? They will be homotopic to each other. Fine. So we use that idea to generate a relation here. So here, if I do X and Y, it would be same as going around Y and Z. Fine. X is the loop. X is the what? X is the line also. I can use X to represent the loop. Concatenation only. Yeah. I mean, I said connecting, but yeah, concatenation. You understood this, how we get that idea. Now, I get this relation y inverse xy equal to z for this crossing. So, if I take a knot and then I start, if I take a knot diagram and then I start writing x, y, z and start for going around each crossing and then saying what is the relation, I can generate a group from that. I can generate the node group just by looking at this, because this will only be the this will be the only obstacles we'll be facing while going around the complementary space, right? Because the cross the we are removing the arcs from the whole space. Only the crossing part will have some problem drawing the loops. And now we found a way to bypass that. If you use this relation, you can just bypass the what the problems, because here x and z was disconnected. There was no way of connecting. I mean, concatenating them. I mean, homotoping them together. But then now I got a relation which has some which connects x and z. Like y inverse xy would be homotopic to the z. Fine. So at the for so you guys know for groups, like there is a generators and relation thing. Okay. So at each arc I'll get a generator, and at each crossing I'll get a relation by using which I can generate the node group. Fine. I mean, now you will be asking, you are looking at a diagram, but knot is in R3. But from the diagram only, you can just take out the knot in R3. Fine? You guys fine with this? Okay. Now, from there also we'll move forward, because, okay, at this point, if anyone is listening, now we don't want to look at that also. Huh. Hmm? It's the inverse direct. I mean, yeah, you can see it as an inverse direction. I mean, I'm taking it as a generator relation thing, right? Hmm? Huh? No, I just need some relation for this crossing, right? And I got one relation. Like I can just write what? Here I can take x inverse this side, and y z x inverse is equal to y. I can get. Hmm? No, no. For a specific node diagram. Hmm. Hmm. Uh-huh. Uh-huh. No, for a I take a node, put it in R3, then take it back. So for that fixed node, I'm getting a fixed node group. Yeah. Mhm. Mhm. I mean, sorry, the node would be oriented. Yeah. The loops. Uh-huh. Yeah, I mean, I take a point outside this R3, like just far away from this node complement and all that stuff, and then start drawing loops. Hmm. Yeah, I'm drawing behind the node. Huh? I mean, that I can just pull back. That I'm not looking at the. I can just say everything else is behind the. See, in R3, it's a, what you say. The problem you say is like when there's a crossing here, how will I work around that, right? I'll just take all the. I'll look at that crossing separately only. Right. I'm just taking the point here so that I can just look at all this. All the upper crossing I can just pull back. Except there will be ones I cannot pull back. That will be going under some other crossing. Right. That I'll get another relation. Fine. Okay. Yeah. So now we'll look at the set of all homomorphisms between the fundamental group, the knot group, and a finitely generated group. I mean, a finite group. Okay, so if when my knot group is finitely generated, right? Each arc will I have finite number of arcs. Each arc will have one generator, so finite number of generators, and if I have a finite group, the number of homomorphism from this to this will be finite. Fine. So this will act as an invariant for groups. Number of homomorphism from number of lambda of okay lambda of G equal to number of homomorphism from some group to G. This acts as a, because if I have two isomorphic groups, the number of homomorphism from both the groups to a fixed group will be same. I have two isomorphic groups, they are basically the same. So the number of homomorphisms will also be the same. So this acts as an invariant for groups. Now, okay. So for the people who have wasted their time through group theory, this looks very particular. This is the conjugacy relation. If I have x and z connected like y inverse x y manner, I say x and z are conjugates. Fine? Fine with that? Okay. So now I start walking through the knot. So whenever I encounter a crossing, my x will go to a conjugate of x. Right? Fine with that? X will go to a conjugate. And then I'll go through z. And then for z also I'll get some relation like this. And then after that I'll be getting a conjugate of z. So I'm keeping on going for these conjugates. So instead of now when I look at homomorphisms, say homomorphism from fundamental group of K to G, not group of K to G, I don't have to I don't like to take the whole group. I just have to take the conjugacy classes. Right? Because only the so if I have a homomorphism phi taking x to some element g, then z will phi of z will be some conjugate of g, right? Some h inverse gh, some conjugate of g. So the whole image set will be conjugates. So we only need to look at the conjugates of g. So instead of computing the whole thing, phi of k comma g, here k is as the knot group. Just think of it as knot group. Instead of computing the whole thing, I can just take the special cases C of lambda k g c. I'll just sum through the conjugacy classes. Right. Now, for the final thing, whatever you want to call. Now, we look at a very specific group called S3. Everyone familiar with this? Symmetry group of order 3, which has elements 1, 2, 2, 3, 1, 3, 1, 2, 3, 1, 3, 2, and what? And E. Fine. Okay. Right. Now tell me the conjugacy class of this group. The conjugacy classes are 1, 2, 2, 3, 1, 3, and 1, 2, 3, 1, 3, 2, and E, right? Look at this. What is 2, 3 inverse 1, 2, 2, 3? I'll get 1, 3. Right. Similarly, what is 1, 3 inverse 1, 2, 1, 3? I'll get 2, 3. So if I have this and this as two sides of crossing, this would be the, this has two sides of under crossing, this would be the over crossing. Now, if I put it for color red, blue, and green, this exactly defines the three coloring. Either I will have 1, 2, what is the relation? 1, 2, 1, 2, 1, 2 will give me 1, 2. If I in the conjugacy class, if I take 1 2 1 2 1 2, I'll get 1 2. Otherwise, for any other element, I'll get the third element. So by doing tree coloring, we are actually looking at the homomorphisms that are going from this conjugacy class. I mean, from going from the knot to this specific conjugacy class. Yeah, specific conjugacy class of S3. And that's how the weird rules why you need three different colors and only one color can come from. And that is nearly 1.5 hours of talk. Thank you. Any questions? Uh, yeah, this one. Yeah, I mean, this will individually define 1 1 1 1 1. So total will be this plus three, three coloring plus three. Any questions other than this? Sorry for the really long explanations. And thank you for coming.